Are we having class on Wednesday?
You mean because of L Day? Yeah. As far as I've heard, I haven't heard them say anything about canceling classes on L Day. I think it's just, hey.
I had to ask you something.
I'm sorry?
I had to ask you something. Is it too late to turn in the paper or no?
No. No.
It's not too late?
Yeah.
Because I saw that I had an incomplete.
Yeah, well, that's probably why. Yeah.
Okay, so if I turn it in, do I just put it in here? Or
You can either bring it up here to the class or slide it in my office door, either one. You know where my office is?
we had this conversation before.
265.
Down that way.
Yeah, down that way. The last office on the left, right before you get to the stairwell, go down, up or downstairs.
Okay, thank you.
Okay, yeah. Right across from the orientation classroom.
Yes, I got you. Thank you.
Uh-huh. Don't understand walking into class for typing session. I guess he thought just two of us hadn't started that or something. But this is the academic the administrative calendar, which most of the stuff on here has absolutely, I don't even know why it's on here or what it's about. But I will tell you a couple of things. on here is listed a Pell disbursement on the 4th, that is Thursday. And I do not know why. That must be second mini-term, I don't know. But they don't specify. But to answer your question, as far as I know, I have heard nothing about canceling classes on Wednesday. I imagine they just figure people can participate in the activities at their breaks and whatever, and free periods.
Well, the reason that I was asking is one person class was canceled.
Oh, really?
Yeah, he said don't worry about coming due to
What was the class?
English 251.
Okay.
Literature.
And who's the instructor?
Kelvin King.
Kelvin King, okay. It may be that he has something he has to do on the Birmingham campus because that's where he's located. So it may be there he has to do something there, so he can't be out here. That would be my guess, but I'll have to check and see. But as far as I know, classes, I've never known to cancel classes at L Day. Okay. But there could be special cases. Next Thursday, the 11th, is Honors and Awards Day. And I haven't heard the times on that yet. It's usually in the morning. And I think it's going to be in the gym. We used to have it out here at Bessemer Civic Center, which is really nice. But I think they've started having it in the gym now that the gym has been refurbished. And it could be that class may start a little late that day, but we will have class. My morning class, I think, will be white slick, but this class, I think the worst would happen that we start a little late. Okay. Then there's things like withdrawal from class and last day of class and that kind of stuff, all coming up at by the end of the month. Actually, final exams start on the 30th, which is a Tuesday. April 30th. Yeah, they start pretty early. Now, if it's second mini-term, they're later, but first mini-term, the first day of finals is then. So our last day of class will be the 29th, which is Monday, because May 1st will be technically finals week. I'll give you the last test for you to turn in and just get it at any time during finals week. Now, this is something that's a bit more appropriate, perhaps, to you. The NASA Community College Aerospace Scholars. You'll see sometimes like that little thing there, it's NCAS. That's talking about that. That's the shorthand for this. NASA Community College, they only put one C, Aerospace Scholars, NCAS. The application for fall 2019 is open now through May 15th. So you have a little over a month, close to 6 weeks, to get the application in. And if you want more information, there was a live seminar last Tuesday. Okay, that was during spring break. They sent the email Tuesday and said there's a seminar this day. Well, I didn't see it. I couldn't have gotten you the information in time anyway. There are some websites you can go to find more information. So if you want to see this flyer, interested in that at all. We've had a few students, I think, from here who have participated in it, and it sounds like they had a great time doing it. They learned a lot. It was just a really fun experience. At the same time, getting hands-on stuff really, it seems like they actually were interacting with something in outer space, whether it was the moon or Mars rover or one of the satellites or something. They were actually doing things with it. I mean, it was really pretty amazing. So anyway, if you are interested, that deadline is May 15th. Okay.
I think NASA's getting ready to go to Mars, aren't they?
Yeah, I believe there's going to be another one. This one they're going to try to use a commercial vehicle, isn't it? Is that the one? Yeah, that's what I thought. But it's not going to be manned, is it? I don't think so. Yeah, it's just I don't think we're quite ready for that. All right, now, what we were doing, any questions before we get started today? All right. What we were doing last time, we were in 11.6. I think I gave you your test for Chapter 11, okay? You probably can't do those last four, I believe it is, but, anything up to that you probably could. But here we're talking about cylinders. And remember, a cylinder isn't necessarily a closed cylinder. It can be an open cylinder. It's any curve, and we're only going to do right cylinders. Any curve in any plane, the right projection from that, orthogonal projection from that follows that curve, that makes a cylinder. Okay? And we did the A one on the top of page 799, example 1A last time. We're doing 1B this time. Z is equal to sine X. Okay? Now, it's hard for me to draw in 2 dimensions. Okay? And so, in 3 dimensions. 2 dimensions isn't, I forgot to turn that on. 2 dimensions is hard enough, but 3 dimensions really gets to be difficult. So, if I can sort of just generally get my pen color, okay, and call this the x-axis, this the y-axis, and this the z-axis, okay? Now, z is equal to sine x. So x is where your thetas will be. Your half theta, quarter thetas, pi. Half pi, quarter pi, not quarter pi. 2 pi, on like that. Okay? And the z-axis is going to be like our y before. So sine starts here at the origin and goes, I'm sorry, I'm going in the wrong direction. Because positive is outward on the orientation I have now, so let me get rid of that.
Towards us.
Yeah, it would be coming down toward me. It's going up here, down here, up here, down here, this kind of stuff. And over here it would be going like this, and like that, and like that, and so on. Well, the cylinder, that is the sine curve on the xz plane, okay? Well, the cylinder would then be all the lines parallel to the y plane that would be going through those various points, okay? So that would be, as you go along here, the line that intersects that. Now, those just look like lines, but this one's intersecting right here, this one's intersecting down here, this one's intersecting here, that one's intersecting right there, here, there, and there. So this is the curve that does it's a sheet. Think of it as a wave that's going like that. All right. And it said, I'm sorry, I thought there was a C here. I wasn't paying attention. It says only from 0 to 2 pi. So forget this, that. Only 0 to 2 pi, that would be this part right here. Okay, so it would be that wave only from here, starting here, down like that. This piece of paper here. Like that, and it's going like this, and then it's down like that. That would be it coming out of the board like that. Okay. People at home couldn't see that, could they? Okay. And you see their fancy little picture on page 799. All right. We get to see their fancy little pictures. I forgot. This is this one. Okay. So the A one that we did last time is the graph is a cylinder whose generating curve is z is equal to y squared, parabola in the yz plane. So if you do it that way, the yz, here's x coming this way, y going that way, z going up. In the yz plane, it's hard to see which way. It's this plane here. This is the parabola in the plane that's right here. You know, the yz plane, that's this. You can look at it, it's going back like this. That's not yz, that's xz plane that way. Yz plane is the one this way. And do they put any limits on it? I don't think they do they? No. Okay, so it goes forward and back. So it would be, if this is the x-plane coming out this way, there's that parabola. Infinitely forward and backwards. This is no limits. So that's the yz plane. See, in two-dimension graph, this looks like it could be talking about this plane going that way, except for this part here wouldn't be colored right. But with this plane, this parabola here, they show it coming forward here for a ways to here, but it could be going back that way as well. So I really don't care for their rendition. Yeah, it's not bad. So it's this curve like that. That's the back part of the curve. Here's the front part. So there is no front or back. It goes infinitely either direction. And then here is the one that we just did. And you draw and this had limits on it, 0 to 2 pi. So it's coming like this, and it's infinitely along parallel to the y-axis. The previous one was parallel to the x-axis. The lines that go through that are all parallel to the x-axis. In fact, the x-axis is the vertex axis there.
And why is it empty? I mean, what's the why? Like, I mean, I guess what I'm saying is that the y values.
Yeah, the y values, since they're not mentioned here, they can take on any value in the world, as long as they fit on that curve, you know. But yeah, y's can go from negative infinity to positive infinity. They just ended it just to show it, but they're infinite in the y's. Just like this one, that's what I was trying to say before, it's infinite on the x's. All the lines parallel to the x-axis, you know, like that.
So where is the y in the equation?
There is none. So that's why there is no y dependence, so it can take on any value you want it to. The x's and z's are related in such a way that that is the functional relationship between x and z, or that one, y and z, I'm sorry. Because x can take on any value. This is one you're talking about. Y take on any value. So basically you draw this thing on the xz plane and then extend it infinitely along y. X and z are limited to those values. Y not limited anywhere. Okay. Now we're ready for quadric surfaces. Okay. The fourth basic type of surface in space, goodness, did I miss the first three? Cylindrical surfaces are one. What's the fourth? I guess we're talking about I don't know. Cylinders are one. Okay, wait, I'm sorry. Spheres are one, planes are a second. Spheres are one, planes are second, cylinders are third, and quadratic surfaces are fourth. Okay, that's it. Okay. These are three-dimensional analogs to the conic sections. So let's do a quick review of the conic sections. Okay? Now, so conic sections, basically your cones, which are structures like this. So certainly lines are actually conic sections, but that's not a surface. Those are just things. Okay? If you cut, and these cones are three-dimensional, okay? Three-dimensional cones. If you cut that cone with a plane parallel to or perpendicular to their axis, then you're going to get perfect circles. Okay? If you cut them at a little bit of an angle, then you get, and these are closer to angles, then you get ellipses. Okay? So circles and ellipses. Okay? If you cut just one of the cone with a plane up here, you get a parabola. Okay? If you cut it, with a plane that goes like this, that's a parabola. Okay? You know, like this. It doesn't cut anything down here, just up there, or just down here. You know, cut a plane along here, and you have a parabola down here, sort of. Okay, those are parabolas. Cut it out either of the axes, and then you get your hyperboles. Okay, and they're always in pairs, because the plane that cuts this way is going to cut the top one and the bottom, and that will be your hyperboles. Okay. So those are the four structures. The circles are basically let me get it referenced correctly. Okay, circles basically are x squared over 8, well, I'm just going to call it r squared plus y squared over r squared is equal to 1. Now, most of the time we say x squared plus y squared equal r squared. And that would be fine. But if you write it this way, and I changed in the middle of my, there we go. This is a little bit more generic. Now these are planes, these are in the plane, not quadratic, not three-dimensional, these are planes, okay? Then ellipses would be x squared over a squared plus y squared over b squared is equal to 1, okay? Here, one of these axes is longer and one of them is shorter, okay? The long axis is called the major axis and the short axis is called the minor axis. They're oval-shaped things. Minor axis here, major axis there, okay? Those are ellipses. Parabolae, I'll put parabolas, but I believe that the plural is something else, is just basically something like this. Y is equal to x squared. You know, that would be the simplistic way of doing it, or written the way we did those, x squared minus y equal 1. And this could have a squared here Yeah, or something like that. But usually parabolas are just written like that. And then hyperbole, I'm going to put hyperbolas, that's what the book calls them, is a lot like ellipses. It's x squared over a squared minus y squared over b squared is equal to 1. Okay. Now, this is your major axes. The way I've drawn this there, that's not quite it. But if that was the x-axis going this way and the y-axis going this way, that would be your hyperbole. If you want to do it like this, then you'd have the plus here and the minus there. So those are the plane shapes that are your quadric surface, that are your conics. They just call them the conics. Okay, so that's what they're saying here. The quadric surfaces are three-dimensional analogs of the conic sections. That's what I was trying to think of, the word conic section. So the equation of a quadric surface, the most generic equation of the quadratics of quadric surfaces would be this: ax squared plus by squared plus cz squared plus dxy plus exz plus fyz plus gx plus hy plus iz plus j is equal to 0. Boy, what a mess and a half. Okay. Now, we're not going to do anything to deal with the cross terms here or even the linear terms here. We're just going to deal with the quadratic terms here and the constant term. And if you move the constant term over there and divide by it, that's where you get your... So there's 6 basic types of quadric surfaces. The ellipsoid, which is like an ellipse, rotated around the major axis. That's an ellipsoid. Hyperboloid of one sheet, okay, that means you have a hyperbola like that, but it's only one sheet, and in the middle is at its smallest ellipse, and then as it gets bigger, going up or down or right or left or however, but it's all of one sheet. Hyperboloids of 2 sheets aren't connected. Those are going like this. If you bring them together and connect them, then it becomes a hyperboloid of 1 sheet. Now, if they only come together just at the point, that becomes an elliptic cone. If it only comes together right at that point, that's a cone. If they come together and do like I was describing before, just get bigger, that's 1 sheet, 2 sheets cone. So they're all related. The elliptic paraboloid, okay, would be a parabola whose cross sections are ellipses, just going in one direction. The hyperbolic paraboloid, however, it's a parabola going this way here and this way there, perpendicular to one another, and it really looks like, to me, a saddle. You know, a saddle straddles a horse this way, but you sit in the thing this way. So, you know, it has a parabola this way and a parabola that way, but they're perpendicular to each other, so to speak. So those are your 6 basic shapes. The elliptic cone is the one that's closest to being just the 2 straight lines that you revolve around an axis. That's your elliptic cone. Okay. Now, the intersection of a surface with a plane is called the trace of the surface. Okay? So you have to almost picture the 3-dimensional structure and then take a plane and cut it. A lot like I was talking about having 2 cones together and having planes cut it to give you your conics. I always go blank on that name. Section, a conic section. Here we're doing the whole surface and taking a plane and cutting it and seeing what that plane looks like. Okay. So the visualized surface in space is helpful to determine its traces in some well-chosen planes, like planes parallel to the XY axis, planes parallel to the YZ axis, and planes parallel to the XZ axis. The traces of quadric surfaces are your conic shapes, okay? Hyperbole, parabole, ellipses, and occasionally circles. These traces, along with the standard form of the equation of each quadric surface, are shown in the following table. Here's basically what we recognize, okay? Here's your ellipsoid. I really don't care for this drawing much at all. This one's much, I think, more reasonable. This is an ellipsoid. However you cut it, you get an ellipse. You cut it in planes parallel to the XZ plane, there's the XZ plane, like this, you get ellipses, okay? This one looks like the major axis is X and the minor axis is Z. You cut it this way, and you get ellipses. This is parallel to the YZ plane. You get ellipses, where the Y-axis seems to be the major and the Z the minor. You cut it, have planes parallel to the XY plane, and you get ellipses. And here it looks like the Y is the major and the X is the minor. Okay? However you cut that in planes parallel to the standard planes, you might say, you get ellipses. However you cut it. Okay? So your traces are always ellipses if they're planes parallel to one of the three given planes. And this is the standard form for it. Now look how similar that is to the standard form for an ellipse. Basically, take a plane parallel to the XY plane, you get ellipses that way. XZ plane, you get ellipses that way. YZ planes, you get ellipses that way. That's what it shows. Eliminate one, and you get ellipses every way. Okay, and of course, A, B, and C can't be zero. Okay, those are your axes. A is the positive value from 0 to the very edge of that one. B is the one this way, and C is the one that way. Okay, and they can't be zero, otherwise you don't have a ellipse. So then here's your hyperboloid of one sheet. Okay, now if you remember what a hyperbola was, it's x squared over a squared minus y squared over z squared, or b squared. Okay. Well, this one you have 1 plus and 1 minus, but they're all equal to 1, just like they were in the other forms I was giving. Now, here's the deal here. If you eliminate the z and cut traces parallel to the xy plane, you get ellipses. You see? This is an ellipse here, an ellipse there, there's one in the center. That's your xy trace. That's what they're called. Now your YZ trace, eliminate the x, and there you have a hyperbola. Okay? And that would be, eliminate the x. So in the YZ plane, see here your hyperbole, like that. If you eliminate the y, so parallel to the XZ plane, these are your parabola, or hyperbole, like that. So in 2 dimensions, your traces are hyperbole. In the 3rd dimension, they're ellipses. Okay, so you have 1 plus and 1 minus. Okay, and that's a hyperboloid of one sheet. Now, if you can imagine tightening the belt, really tight, you get a smaller and smaller and smaller ellipse here until you get a point there. Okay. And when you get the point, you basically have your cone, elliptic cone. You don't have hyperbole anymore this way or that way because they squeeze down to nothing. But your the XY traces parallel to the XY plane are all ellipses, okay? Now, if you come away, if you're right on the XZ axis or the YZ axis, those traces are just straight lines, okay? But if you come away from the XZ, something parallel to the XZ axis, say, coming out this way or going back that way, now you get your hyperbole again, okay, as you come out this way or go back that way, or when you do your traces this way, parallel to the YZ plane and come out the X, you get hyperbole that way too. Now, the difference here is you go to 0 here, okay, because you tighten the belt till it's 0 in the middle. All right, now you look at that and say, but there you're back to a +1. Well, if you change your signs and made a minus plus plus, that looks just like the hyperboloid of one sheet. Only thing is this becomes a -1, which means they're separated. Okay, so there is an area in there, and the separation occurs where these signs are the same. So the Z, here's the other way to look at it. So much better if they wrote it the way I was suggesting. To me, it's easier to see that way. But for any X's and Y's small well, if you eliminate this one in the XZ plane, you have XZ plane, that's this one, you have hyperboles, of course, and the YZ plane, you have hyperboles, of course, okay? But when you do the XYs, parallel to the XY plane, if these X's and Y's are too small. Let's see, is that right? No. When you put X equals 0, Y is equal to 0, then Z is equal to C. Do you see that? When X's and Y's are 0, or small number, let's do 0 first, your Z has to be plus or minus C. Plus C up here, minus C down there. You don't have anything in between plus and minus C. Okay? And for small enough X's and Y's, then you get nothing in there. When X's and Y's get a little bit, or Z gets greater than C, then you can start having X's and Y's. So it doesn't matter how big the X and Y are, but Z has to be greater than C. See, that wasn't the case for the one sheet, because in the one sheet, everything still gives you, you don't lose any values. You when these are both 0, you're at plus or minus A here, and these are 0, you're at plus or minus B there, Y is plus or minus B. Here, Z is plus or minus Z. When these are plus 0, this never happens. And you notice that you never get X and Y both being 0 at the same time, because then that's an undefined situation. You can't have a negative Z squared over C squared equal 1. It just can't happen, ever, okay? So that's why there is no, the belt doesn't tighten all the way. When the belt does tighten all the way, then that becomes a 0 here. And when it separates, then you have both minuses there, and that never happens except z is plus or minus c, and they go from there. So anything between plus or minus c is not there. But again, you have hyperbole cut this way or that way, this way, that way. All of them form hyperbole. But this way, they're still ellipses. And if they're exactly the same, A and B are the same here, then those are circles, not ellipses. Well, ellipses, circles are ellipses, but not all ellipses are circles. So you see your basic form is just about the same. Okay. Now, two more. Your paraboloids. Your elliptic paraboloid, when you cut them parallel or perpendicular to the axis, you get ellipses. That's why it's elliptic paraboloid. And you get parabolas any other way you cut it, this way or this way, they're always parabolic. Okay? So that's your elliptic parabola. I think I see why they have this form now. This is taking a parabola and rotating it around the z-axis. So let's go back and see if that fits for here. This is taking a hyperbole and rotating around the z-axis. This is taking hyperbole that touch, you know, and that's what gives it a cone. And this is taking an ellipses and ellipses here, ellipse here, and rotating around the z-axis. And that's why they showed this. You see, here there's no difference from rotating around this one or that one, and therefore it made it, why did they choose the z? Because it was vertical, I guess. But this one, you take a hyperbola and rotate it around the z-axis, and you got this shape. But this hyperboloid of two sheets, you're taking these hyperbola and rotating them around there. This one, you're taking these hyperbola and rotating them around, not the other one. So that's why they have that. That's why when I first looked at that, I thought these were rather bizarre. But this is the weird one. I call this the saddle. You can almost picture the horses under here and you're over here. Okay, so that's how I look at them. Any way you cut it, okay, it's a paraboloid. So two ways you cut it, they're paraboloid. But the third way you cut it is a hyperbola. Okay. Now you might have trouble seeing the hyperbola. On these pictures, they really are hard to see because they don't do the slicing very well. But you have parabolae this way, and you have parabolae this way. You can see those. What you can't see are the hyperbolas. Okay? Now what you get with that one is if you cut on the z-axis this way, then you have this one's curving out like this, and that one's curving out like that. So that's the hyperbola there, parallel to the xy plane. Up here, they're doing like this. And down here, they're going like this. So again, they reverse. But the other two ways, they're parabolic. And similarly, the paraboloid, one of them is to the first power, just like a parabola was. The others are to the second power. The elliptic parabola, when you wipe out the z, that's your ellipse. And this one, when you wipe out the z, that's your hyperbola. Okay? So therefore, that's why they get the names like they do. But nothing's being, this one that is revolving around here, that parabola is being revolved around the z-axis, and that gives you an ellipse that way. This one, nothing's being revolved around an axis. It's doing different things around two axes. Okay? But those are your general equations. All right. So, it says classify and sketch the surface. I'm not much at sketching these, okay? So what I'll do is refer you back and say it's going to look sort of like this, okay? But here's how you classify them. Okay, you got this one up. Is that what you're working on? Okay. Get all your variables on one side. 4x squared minus 3y squared plus 12z squared. And make this equal to minus 12. Okay? Get something on the other side, your constant on the other side. Okay? Then divide everything by the minus 12. Okay, now what do you have? You have x squared over minus x squared over 3, right? Plus y squared over 4, right? And minus z squared over 1. I just put that in, is equal to 1. Which of the shapes is this? I'm going to do one other sort of, you might think of it as a dumb thing, but I really find it useful for me. And I'm going to put the plus in front. Y squared over 2 squared, I'm also going to do that, minus x squared over root 3 squared, minus z squared over 1 squared is equal to 1. Okay. Now, what this does for me is get it back sort of in the standard form. Okay? If you recall, the thing with 2 minus signs in it has to be that hyperboloid of 2 sheets. 2 minus signs, 2 sheets. Hyperboloid of 2 sheets. So the y-axis, they usually draw it going this way. That's the central axis of this, and you'll never get closer than plus or minus 2, okay, to the center. That's how far apart the 2 sheets are. 2 on this side, 2 on that side, so 4 units apart. Your x squared like this, and your z squared like that, you know. So that is your hyperboloid, because this makes a hyperboloid, and that makes a hyperboloid, okay? And if you did that, and then moved the minus sign, you would have ellipses out here, but they would be outside. So this would be basically, let's go back. There's your hyperboloid of 2 sheets, okay? But it's turned along the y-axis. So one of these dishes are out here and one of them's over there. Does that make sense to you? Okay. All right. So I'm going to let them do the drawing. I'll just change it around a little bit. All right, does that make sense? And you see, these are ellipses here. You get from letting that be 0. It's just that they're not always 1. Basically, you have to get z over c greater than 1. And any time that z over c is greater than 1, then you have an hyperbola there. An ellipse there. In between z over c less than, z over c less than 1. In other words, if c is greater than z, you don't have anything z is too small. When z is big enough, because c is fixed, when it's big enough, then you start forming your ellipses. Okay. All right. So that was that one. So let's clear this and let's see if they'll draw the picture for us. I'll let them do it. Okay. Begin by writing the equation in standard form. That's not it. Okay. Well, I don't know. Let's go back and see. Did they call this? No, it's not the standard form. This is the general form. So what we had was general form. Okay, the standard form is, like I said, moving the, they haven't done it yet. This is general form here. That's in general form. No cross terms, no linear terms, just that. Okay? Move the constant to the other side and divide, oh goodness, by minus 12. I would have moved it and then divided. They divided first and then I'm going to move it and make it look like that. Okay. And they also moved the plus term just like I did here. Now this is a squared, that's b squared, this is c squared. No, this is a squared, that's b squared, that's c squared. 1 is c squared. I want to go and put it over 1 to make it more realistic. Okay? And then that forms, you can conclude that the surface is a hyperboloid of two sheets with the y-axis as the axis. Now, if you've been wondering what would happen if you kept those cross terms in there, the dxy and the z, e, y, z, and those terms, then you take the axes and you twist it. It's no longer along one of the, main axes. It now twists and goes somewhere else. And then if you have the linear terms in there, that shifts the origin. So the center is no longer at the origin. See, all the ones we're doing have the origin at the center of them, and everything is along one of the other axes. Okay. We don't want the others. Okay, please don't let's have the others. Okay, so to sketch the graph of this, it helps to find traces on the coordinate planes. So the the xy trace, that's with z is equal to 0, you have this situation. Z is equal to 0. Those are all hyperbolas. Okay? And, they, on the xy plane, are going like this and, like this and that, because y is the major axis and x is the minor axis. Okay? So that's how they look. And the xz trace, those are your, when y is equal to 0, there is no trace. At y is equal to 0, it doesn't happen. Okay? Now, if you get y big enough, greater than, so y over b is greater than 1, then you get traces of ellipses, but only when you get further out on the y-axis. Okay? And then where on the xz trace, where yz trace, where x is equal to 0, you have hyperbola again. Okay? And that time, the traces along, again, the y-axis is the axis, and the z's are like this. So you have hyperbole this way and hyperbole that way. Okay. That wasn't quite shown right, but that's what you got. Hyperbole this way and this way. Okay. When y is equal to 0, you don't have anything, because you have a negative number equal to a positive number. Not going to happen. Okay. So it goes to minus 2 to plus 2 is before you finally have action there on the y-axis. And anything outside of plus or minus 2 for y, then this thing is greater than that. So now you can have, move this over here, that would give you a positive number, move those over there, that would be positive, and those are your ellipses you have this way. Okay. Make sense? All right. Now, we skipped example 3. So let's go back and do example 3. All right. Oh, excuse me. Here's what we have. X. All right. Let's see. Now remind me, you did ask me for a letter, right?
Yes, sir.
Okay. I've got it on my computer. I just hadn't printed it because I want to make sure you're the one who has it. I was certain of you. You didn't ask me for a letter, did you? Okay, right. I was contemplating at home saying, who was the other one? I think I know who it was, someone in my pre-calculus algebra class. One guy I know, he was, which class is he in?
Where are the letters for?
Huh?
Where are the letters for? I might need one.
For the, is it only summer scholarship or is yours for next fall too?
It'll be for next fall.
Next fall,
Yeah.
okay. I didn't specify this, I just said scholarships.
Okay.
Because I couldn't remember which yours is
Yeah,
for.
it'll be for the fall.
Yeah.
But if they give me the summer that, I mean, I might use it.
Okay. Are you planning to come this summer?
If I can, I mean, if it's paid for, I just wouldn't be able to pay for it this summer because I would work the summer to pay for the fall.
Right, I see. Okay. That's what it was scholarships. Now I'm going blank. I could remember 2 out of 3 at home. I got yours remembered. Oh, I know who it is. Yeah. Jake Dove. But the third one, I think, is Cameron Church. But I'm not sure. That's who I wrote it for. But if it's not him, I'll have to find out who the third. That's why I asked you, make sure it wasn't you. Okay. All right. We're doing example 3 on page 802, chapter 11, vectors in the geometry of space, 11.6 is surfaces in space. And were you here the last class? Did you get the test on chapter 11? Okay. Okay, before you leave, get it. Okay. Did you say you might go to the Birmingham campus that Friday? To pick up the test? Somebody had told me that, and I took it over there, and they never showed, but I couldn't remember who it was.
I don't know if I said that. I can't even remember.
I can't remember either. I couldn't remember who it was.
I don't know if I said it. Don't worry.
Well, somebody said it, and I stuck it in, and then when I got over there.
I was supposed to meet you at your office, like right here.
Oh.
You said you was going to come, but I think somebody came in and started talking to you.
Oh, I see.
So, yeah. I was like, okay. Because I had waited there for him, and I was like, he might be here. Because I knew you had lunch, and like you had another.
Oh, okay. Well, you could, just to pick up a test, you could have come in.
I was like, if he don't get to make it here right now, he won't be able to.
Right, that's all right. All right. Here's example 3 on page 802. Classify and sketch each surface. X minus y squared minus 4z squared is equal to 0. Okay. Now, any guesses right off the top? Basically, it says the same thing as this. Classify and sketch the surface. So the same instructions there go for this one. What would you say the surface was? The only one that has something to the first power, just like the only one of the conic sections, is the paraboloid. So now it's figuring out which paraboloid. Okay? So what you do is keep the x on one side and move the other to the other side, and you have x is equal to y squared minus 4z squared. Okay? Equals 0. Oops, plus 4z. Wait, I don't have an equal 0 there. I don't know where. It must still be spring break. Oh, I was going to tell this. Oh, I already asked you, didn't I? Yeah, never. What, the past tense? Yeah, okay, never mind. I already did that. Okay, never mind. So, when you write it this way, hopefully it becomes clear which paraboloid, because you have one thing to the first power, which paraboloid you got. that would be,
Y squared.
yeah, with the plus in there, that's an ellipse. You could divide everything by 4 if you wanted to, make it a little more reasonable looking. And then you have 1/4 x, which doesn't really matter, y squared over 2 squared plus z squared over 1 squared. That now, if this is 1, that's an ellipse. So this is an elliptic paraboloid. Okay, the elliptic paraboloid is basically a parabola that you spin around the x-axis. So that would be, the x-axis is here, y and z are, let's use this x-axis here, y and z are there. So this would be the parabola that's described there, spun around the x-axis. Okay? And if you look in your book, that's what you see. Now they leave it, their standard form, they don't do this, they don't divide by 4, they leave it just like I had that without dividing by 4. Okay. Now, what basically gives this away is have x equals 0, you get ellipses, or say x equals 4, you have ellipses, okay? That would be the standard form there, x equals 0 in this, or 1 in this form, that would give you ellipses. Y is equal to 0, you have a parabola around the x-axis, z squared, and have here you have a parabola around the x-axis again in the xy plane. So that gives you a elliptic paraboloid. Okay, so you can sort of see their names there. And here's Daniel. Now, you're coming back, okay.
Yes.
All right. Any questions on example 3 then? Okay. I think there also is skipped example 4, so let's do that here too. If there's no question, I'll erase this, right? Okay. So let's do this one. Classify and sketch. Oh, I said we weren't going to do this, and they did it. X squared plus 2y squared plus z squared minus 4x plus 4y minus 2z plus 3 is equal to 0. Now that would be the general form. Now notice we still don't have any xy terms, yz terms, and xz terms. Those aren't here. Those are the ones that tilt them and they're not going along a major axis. Not going to do those. But they have included the linear terms here. What do those do for us? Well, here's what you do with them. Get your x's together. X squared minus 4x blank plus 2y squared plus 4y blank, pretty obnoxious blank, isn't it? Plus z squared minus 2z blank is equal to minus 3. Again, put the minus 3 over on the other side. Okay. Now, what you do at this point is, our favorite of all time, complete the square. Okay? On this one, to complete the square, what are you going to have to add? Remember how you complete the square? Take half of the linear coefficient, that'd be a minus 2, right? And square it, plus 4. Well, you just added plus 4 to that side, so you got to add plus 4 to this side as well. Otherwise, it's a different equation. Okay? Now here, we first factor out the 2 and have a y squared plus 2y. Okay? Whoops. I forgot my blank. Okay? They're really obnoxious, aren't they? Okay. Okay. Now, we need to complete this square as well. You take half of this, 1, and square it, and you get 1. So that's plus 1. But actually, you added 2 here because you have a 2 out in front of that. So you have to add another 2 over here, right? Okay? And here, to complete the square, it's half of minus 2 is minus 1. Square it, you get a plus 1. And that's just a plus 1, so add another plus 1 there. Okay. So, what do we have? X minus 2 squared plus 2 times y plus 1 squared plus, yes. Where'd the plus 2 come from? Right up here?
No,
Oh, here?
no, negative 3 plus 4 plus 2 plus 1 plus 2.
Oh, okay. Okay. Remember, we factored out the 2 here, and we left a y squared plus 4, plus 2y, blank, remember? Okay. Now, you complete this square, which is half of 2 is 1, squared is 1, right? But you got a 2 in front, so it's a plus 2 here. By having 1 there for the 2 in front, you added 2 to this side.
Oh, right.
So you have to add 2 on that side as well. Okay? And then this one becomes z minus 1 squared is equal to 4. Right? Because this is minus 3 plus 3. That leaves you a 4. Right? Yes, sir. Okay. Pardon me? At 320, yeah. Yeah, 320, you're right, yeah. 310. 210. Height. Okay. Something. 210. I don't have my watch anyway, so I'll just go until y'all start leaving. No, don't get any ideas. Okay. All right. So what do you do? Divide everything by 4. Okay. This will become a 2 then. Okay. And this becomes a 1 then. So what you have now is x minus 2 squared over 2 squared plus y plus 1 squared over root 2 squared plus z minus 1 squared over 2 squared is equal to 1. Okay. And first, tell me what kind of quadric surface that is. Classify it. All pluses. Huh?
It's going to be a ellipsoid.
Ellipsoid, because whatever you call it, you still get an ellipse. Every dimension you get ellipses everywhere. So that's going to be an ellipsoid. Here's the difference, though. The location of the center of this ellipse is going to be 2 minus 1, 1. So you go 2 out the x-axis, positive x-axis, minus 1 on the y-axis, and plus 1 on the z-axis. That's going to be the center of this ellipse. And the x and the z axes are going to be equal with the y being shorter. So you're going to have a football-looking type thing. It won't quite look like a football. It's sort of the reverse of that. But you see the picture. It really looks more like an Easter egg since that's coming up soon, except it's pretty symmetric. It's not as pointed as a football field. A football would be. look in the book. I'm not going to draw it for you. Okay, but you see you come up positive x-axis 2 spaces, back on the y-axis 1 space, and up on the z-axis 1 space. And then these gives you the length of your axis. This goes from -2 to +2, -√2 to +√2, and -2 to 2 on the z. And that gives you what you got there. Does that make sense? So you see what you do. You get your variables together and then complete the square, factoring out any factor for your quadratic term that is not 1. See, this is 1, that's 1. Those are fine. This is 2. So you factor out 2 out of both of those terms before you complete the square. But then when you do complete the square, whatever you add here, and there's always an add. Whatever you add here, you have to multiply it by the number in front. Here you just add that number and that number. So it's ones in front. And that gives you an ellipsoid. If one of these had been a minus, what would that have been?
It would have been a
elliptic.
cone.
No, 1 to 0. 1 or minus. That would have been an elliptic hyperboloid of 1 sheet. Only 1 minus sign. If 2 of these had been minus signs, then it's an elliptic paraboloid of 2 sheets. And if one of these had just been to the first power, that would have been a paraboloid. Okay? Now, to get the cone, let's go back to the cone. If that had been a cone, then that would have been, had to be a -1 over there, and then 2 of these would have been minuses. I believe that's right. No, it would have been a 0 over there. I'm sorry, a 0 over there, and it didn't matter what these were. But if you have a 0 over there, that would be because you have a 0 radius at the middle. Okay, your belt is completely tight, squeezed into 2 cones. Yeah. Okay. And if one of those would have been to the first power, that would have been a paraboloid. But you have 2 types. If the other 2 are the same signs, that's a elliptic paraboloid. If they're of different signs, it's a hyperbolic paraboloid. I think I said that right. Okay. Go back to this. Yeah. If the z or whatever is equal to, if the linear is equal to the sum of the 2 quadratics, that's a elliptic paraboloid. If the linear is equal to the difference of the 2, that would be the hyperbolic paraboloid. Okay, so that was example 4. All that was a translation when you have the linear terms there. If you don't have linear terms, the center is at the origin. If you have the cross terms, which I hope we're not going to do any, those would be, that means your axis is not along one of these axes. All right, now we move to, any questions on these before we move off? Okay. Surfaces of revolution. My wife and I got to go see Hamilton in New Orleans over the weekend. The revolution, so I'll be thinking of that. I'll start singing. No, I won't. I'll promise you that. I don't want that bad of evaluations. Okay. So, surfaces of revolution. The 5th special type of surface. Going back, your first type is a sphere. The second type goodness, why do I always forget the second type? The surface. planes, of course. The third type is your cylinders, and the fourth type are quadrant surfaces. Here's the fifth type. Fifth special type of surface you'll study is a surface of revolution. Now, we've done these in earlier courses, maybe even some in this one, but I think it's earlier courses. We'll now look at a procedure for finding its equation. Let's consider the graph of a radius function, y is equal to r of z, okay, in the yz plane. That's going to be your generating curve, okay? Your radius is going to be some function of z, okay? So let's put the y orientation like this, the z orientation like this, and that's going to be your generating curve. So y is some function of z, so it could be doing that kind of stuff, whatever it's doing. Y is a function of z. No, I've said it backwards. That would be doing like this, because your z would determine what your y is. So z is the independent variable, y is the dependent variable. Now, you're going to rotate that. That's going to be the generating curve in the yz plane, and you're going to rotate that when this graph is revolved around the z-axis, that was your independent variable, it forms a surface of revolution as shown here. So like I said, here was the original curve. Y is a function of z. Pick a z, it gives you your y. And that's going to be revolved around the z-axis, but that's why we call it the radius function. See here, that's the radius, there, it's the radius, there, it's the radius, there, it's the radius. So the key here, this has to stay strictly positive or strictly negative, the y does, okay? Otherwise, if it crosses, then you've got some weird kind of things going on. The trace of the surface of the plane, z is equal to z0, is a circle whose radius is that value. So, I'll show the z0 here. Let's just say this is the z0, then that's the radius, there's a circle that you rotate around the z-axis, okay? Whose equation is x squared plus y squared, that's the circular formula here, is equal to r squared, which is that r of z0, that's that radius, whatever that value that is, squared. Now, replacing z0 with z produces that, okay? And that's pretty much what we've got here then. This would be the generating circle. X squared plus y squared, that tells you it's going to be a circle, and that's going to be some function, perfect square of some function. Okay. In a similar manner, you can obtain equations for surfaces of revolution around the other two axes shown here. Y squared plus z squared is some function of x squared. X squared plus z squared is some function of y squared. And x squared plus y squared is some function of z squared. So there's the three. Okay. If the graph of the radius function is revolved around one of the coordinate axes, then this is what you've got. Okay. Remembering these things here, before you square it, these things generally are all positive. They need to be, otherwise they get a little squirrely. Okay? So it says, find an equation for the surface of revolution formed by revolving this graph. There's your y as a function of z, about the z-axis, because this is the independent variable, that's the axis you revolve around. Now, what you have to do is keep z's positive. They certainly can't be 0, of course. So let's just keep all the z's positive. And there's that's going to be a curve that goes like this. You revolve that around the z-axis, and you're going to get a megaphone, type looking graph. Okay? Now this one, it says revolving around the y-axis. Well, that means the y needs to be your independent variable, okay? So that means you have to take a square root of both sides, and that would give you 3x is equal to y to the 3/2 power, and then divide by 3. So y to the 3/2 divided by 3, that then is going to be your radius function. Let's That's a little bit of arm waving here. By the way, you're not tested on this, so that's why I'm going through this one a little fast. So there's your radius function here. This one you have to be able to write it like that. Now they're going to do it, it looks like well, I think they'll still do it. Okay. Did I miss something here? Oh, okay, no. This is just doing the A one here. So the A is going to be x squared plus y squared is equal to 1 over z squared. That's what we're going to do here, okay. Now the second one is this one, and you, again, get x as a function of y because you want the y to be the independent variable here. So like I said, you took the square root of both sides, and that gave you 3x is equal to y to the 3 has power divided by 3, so it's 1/3 y to the 3 has power. That's the R function. Then to get the surface of revolutions, x squared plus y squared, x squared plus z squared is equal to that thing squared. So it would be 1/9 y cubed. X squared plus z squared is equal to 1/9 y cubed. So there's that equation. That's the surface of revolution. On this side is always going to look like a circle. Okay? That side, that'll give you the radius of the circle. And there's another megaphone. Okay. There. I don't think they showed the first one, did they? I don't recall that they did. Let's go back. Did I miss it? No, they didn't show it. Okay. But here's that one. Okay. And that's it. Now, you can do some of these exercises as you want. Some of these you have to do. So, by all means, I would say do all 5 through 10. The answers in the back and the descriptions are at Calc Chat only for the odds, 5 through 9. But try to match up those. You should be able to do all 5, how many is that? 6 of those, but only the 3 odds are in the back. Then do either 11 or 13 or both. They're both at Calc Chat. 11's at Calc View. Do any of the odds, 15 to 25. They're all at Calc Chat. 17's at Calc View. And you can do 27 and or 29 if you'd like. Okay? Now the others, I'll let those be up to you. Because those are all the surfaces of revolution, and then volume of a solid. The analyzing a trace, you should be able to do 43 if you would like. And the surfaces, you don't have to do those. 49 is one you should be able to do. You could think about doing 51 if you'd like. We're not doing 11-7. Okay. Are we running out of time, or you just have to leave out? Okay. All right. So the others of you have to let me know. We're going to move on. We're going to skip 11-7. Huh? Why? We don't have time. Okay. Because we need to move on to chapter 12. You needed to have quadratic surfaces, but the other, it's good stuff. It's vectors. It's cylindrical and spherical coordinates. They are good things. If you need them, by all means, you know where to look for them. Review exercises at the end of the chapter. You can do any of the odds here. They're all at Calc Chat. 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23, 25, 27, 29, 31, 33, 35, 37, 39, either 41 or 43 or both. Then any of the odds 45 through 47, 45 or 47 or both. Any of the odds 49 through 57. Okay, they are all those I just said were count chat. 59's there. 59 is a surface of revolution. You don't have to do that. And you don't have to do any beyond 59. There's a problem solving. If you want to look at that, you certainly can. Don't have to. Okay. That finishes chapter 11. Now, did you get a test for 11 last time? Daniel? Yeah, chapter 11. Were you here the Wednesday before spring break? Okay, did you get a test?
Yes, I got it.
Okay. You said you didn't, right? Okay. Hey, looky here.
I just got off work. I was trying to rush to get over there.
Okay.
Working in Phil City.
Okay. You probably didn't get a test.
Yes, sir. I got it.
Okay. I'm trying to find it. I just had it. It's in here. I know it is. All right. This is it. Yeah, one for each.
Oh, okay. I did.
This is the chapter 11 test. It's only 1 through 6. It doesn't do 7.
So we have some questions 1 through 6.
No. Sections 1 through 6
Oh, okay.
in chapter 11. We didn't do chapter 7. The last 4, 7 through 10, are quadrant surfaces sections. 11.6. The others come from the first 3. First 5. So I think it's 1 each from 11, 1, 2, 3, 4, 5, and then the last 4 from chapter 6. I can't get this to do. I keep hitting the wrong keys. Okay. So that finished what we're going to do in 11. You've gotten the test now. And you did get it, right, Daniel?
Yeah.
Okay, good. All right, so now we're going to move to chapter 12. Okay, and we'll go from current slide. And chapter 12 is entitled Vector Valued Functions. Now, y'all are going to have to keep up with time. How much time do we have now?
10 minutes.
10 minutes? Okay. 12.1 is called Vector Valued Functions, okay? What we're going to do here, and this is a fairly short, a little bit shorter section, only 5 sections here, but we're going to do some of everything here. We'll analyze and sketch the space curve given by a vector valued function. We'll extend the concepts of limits and continuity for vector valued functions. All right. So, space curves and vector valued functions. The first subtopic in 12.1. A plane curve is defined with a set of ordered pairs f of t, g of t. When you have parametric equations, that's how your x is f of t, your y is g of t. Your independent variable is t. Your x and y are intermediate variables, and then your the curve itself is your dependent variable. Okay? Together with the defining parametric equations, where x is f of t and y is g of t, where f and g are continuous functions on t, of t on some interval I, and that interval is of t, not of x and y, but of t. That definition can be extended naturally to 3-dimensional space to define a space curve, and this is called capital C. Okay? And the space curve, capital C, is a set of all ordered triplets, f of t, g of t, h of t, where this is x, y, and z, together with the defining parametric equation, x is equal to f of t, y is equal to g of t, and z is equal to h of t, where f, g, and h are, again, continuous functions of this independent variable t on some interval I of t. That t is in I, not x, y, and z in I, but t is in I. The new type of function is called the vector valued function is introduced. This type of a function maps real numbers to vectors. Okay? You give it a number, and it comes out with vector. Okay? You put in the meat grinder numbers, and you turn the handle, and what you get are vectors coming out. A function of this form, r of t, okay? Now, doesn't necessarily mean a radius, so don't think of that, but it's some spatial feature. R of t is equal to f of ti plus g of tj, x, y, okay? Now, or, that's in the plane, in 3 space, it would be r of t is f of ti plus g of tj plus h of tk, x, y, and z. That's a vector value function where you see you feed in a t, which is just a scalar value, just a value, and you spit out a vector, either 2-dimensional or 3-dimensional vector. And these vector value functions, where the component functions f, g, and h, are real valued functions of the parameter t, independent scalar number t. Vector value functions are sometimes denoted this way. R of t is angle bracket f of t comma g of t if it's in the plane. R of t is f of t, g of t, h of t in angle brackets if you're in space. Okay? Now, notice these are still parentheses around the t. The angle brackets are only on the outside. Okay. Technically, a curve in the plane or in space consists of a collection of points and the defining parametric equations. Okay? 2 different curves can have the same graph. Okay? For instance, if you had r of t, there's your vector value function. Let's say, if I'm writing this, I put an arrow over it. If I'm typing it, I'll do it bold. Okay? Sine of ti plus cosine of tj. Okay. But if you had done this one, r of t is sine of t squared I plus cosine of t squared j. Each of those curves has a unit circle as its graph, but the equations do not represent the same curve because the circle is traced out in different ways on the graph. On this one, you start out when t is equal to 0, sine is 0, so your x value is 0, your y value is 1, because cosine of 0 is 1. And then as you increase the t, you're moving around like this. Yeah, it's a circle, and that in the first quadrant, it's going like this. This one, when t is 0, you start at 0, and this one you start at 1. But then you only get, I think, a quarter of the way or halfway down the first quadrant before, by the time you just do this. So, same unit circle as its graph, but the equations do not represent the same curve because it's traced out in different ways, different characteristics there. All right. Be sure you see the distinction between vector value function r and the real valued functions f, g, and h. Okay? Vector value comes out of vector. F, g, and h are independent functions. All the functions are of the real variable t, but r of t is a vector. F of t, g of t, h of t are real numbers, not vectors. They form the components of the vectors. Real value functions are sometimes called scalar functions to distinguish from vector value functions. So these would be what we call scalar functions, but they form the components of a vector value function, r of t. Vector value functions serve dual roles in representing the representation of curves. By letting the parameter t represent time, you can use the vector value function to represent motion along a curve. Okay? So your r of t would be your displacement vector. Not a radius, but a displacement vector. And then you can take a derivative of that and have a velocity vector, and a derivative of that, and you get an acceleration vector. Or, in the more general case, you use the vector value function to trace the graph of a curve. Okay? It doesn't represent the motion of the curve, it actually traces the graph of the curve. That's what I was doing before. I said it starts here and moves down this way as t went from 0 to pi halves. Now, in either case, the terminal point of the position vector r of t coincides with the point xy or xyz. In other words, your position vector r of t, wherever its point is, the end of it is, wherever that is, that's going to be the value of that function at that value x, y, and z, determined by the parametric equations. So, now this is a curve in a plane. If you're at t0, if your x value is negative, your y value positive, you'd be right there. At t1, you'd be over here, x positive and y positive. T2, you'd be over here, x positive and y positive. Those would be the three positions of the vector function. Here's that vector, and that vector. What they're tracing is the curve C. What they're tracing is the curve C. In 3 space, you have 3 dimensions here. Your r of t1, your x would be here, y is 0, and your z is up here. So that's your vector here. And this one, your x is over to here, your y is over here. So your x is out here, y is here. No, I'm sorry, y is there. X is here, y is there, and z is up here. And on this one, C, point C, your x is 0, your y is here, and your z is up there. So this will be a curve that goes like that, okay? Leaving the wall here and going up and over to the wall here, okay? Something like that. The curve C is traced by the terminal point of your vector value function. The arrowhead on the curve indicates the curve's orientation by pointing in the direction of increasing t. Now, which arrow are they talking about? This arrow. This is saying as you go from T1 to T2 to T3, you're going along the curve like this. If you're going from T1 to T2 to T3 here, you're going in that direction. So that arrow, not these arrows, that's the terminal points. This arrow here shows the direction of increasing t, okay, for your vector value function, okay. That's the arrowhead they're talking about. Unless stated otherwise, the domain of a vector value function R is considered to be the intersection of the domains of the component functions f, g, and h, okay. So, if this is your function, r of t is log t I plus square root of 1 minus tj plus tk, what is your domain of this vector value function? Well, it has to be the what's in here and there. Let's start with that. Any t in the world would be fine there, okay? But not here. What's the limits here? So the domain of log. T. What values can t take on? Only positive values. You can't take the log of 0, you can't take the log of a negative number. They don't exist. So this has to be t greater than 0. Greater, not greater than equal, greater than 0. For this one, what you know has to be true. T has to be less than or equal to 1. If t was anything greater than 1, then this becomes negative, right? You can't take the square root of a negative number, okay? So here, we know that t has to be less than or equal to 1, okay? A negative 12 will be fine here. That would be 1 minus 1 minus 12. That's 1 plus 12 is 13. Square root of 13, I don't know what it is, but you can do it. It can't be a positive 12 because 1 minus 12 is minus 11, and that would be, you can't take the square root of a negative number. So this has to be anything less than or equal to 1. Well, with this having to be greater than 0, less than or equal to 1, this could be anything in the world. That's what you're limited to. You have to be between 0 and 1. You can be 1, but you can't be 0. So it's open parentheses, 0, comma, 1, close bracket. Anything between 0 and 1 is all you could possibly have. All you could possibly have. Because to be on that curve, everything has to be defined. Those are the only values of t where that will be defined. So you'll start at 0, but you won't put a 0 in because you can't put 0. But start anywhere just beyond 0, 0, 1, however small you want to be. This is going to be an incredibly tiny number. I mean, negative number. Very, very negative number. So it's going to start on very negative i's, way, way, way back there. And then at t equals something just beyond 0, this is going to be awfully close to 1. So your y value is going to start at 1. And your z value is going to start very close to 0. So you'll be somewhere way back there, there. And then as this increases up until 1, when this reaches 1, you're at 0 on x. So you're only going to make it to the origin on x. And this will go to 0 on y, and this will go to 1 on, so it's going to end up 1 unit up here. 0, 0, 1 is going to be your terminal point. Your initial point is way back there at a very, very, very large negative number, close to 1 on the y-axis and 0 on the z-axis. So it's somewhere there. So that's going to be it's going to be a pretty long curve because it goes so far back on the x-axis, but it's going to stay between 0 and 1 on y, and between 0 and 1 on z. All right. Did they just skip 1? I think they did. So let's go back and do example 1. Well, they don't give us any place to do example 1. So we'll do example 1 here before we do example 2. How much time do we have? Is what?
3 minutes over.
I can't hear.
3 minutes over.
Oh, we're over. We'll start at example 1 next time. Okay, sorry about that. All right. No new homework problems in this section, but you got plenty to finish up on example in chapter 11, and you got the test in chapter 11.
Yeah. You said that the test was on chapter 11?
The one I just gave.
Yeah.
That's on chapter 11. Yeah. 11:1 through 11:6. 4 of the questions are 11:6. The other 5 are 1 each from each section, I think.
11.1 to 11.6.
Yeah. All right. I forgot to mark Charles when he came in. Let me get you now. And the others didn't show. All right, good deal. We'll see you Wednesday then. All right. Any other questions?
Did you say that we were only going to do 6 questions on one of those? Or
I'm sorry?
you said we were only going to do 6 questions on one of those tests? Or was that?
No. I said that when I gave it out to you on Wednesday before spring break, I said you can only answer the first 6. The first 6 are from the first 5 sections. So there's one section has 2 questions on it. I said you can only do the first 5 now. You'll be able to do the other 4 after we have class today. Now you can. Yeah, you do them all. But when I gave them to you on Wednesday before spring break, I said we've only covered in class the first 6 at that point. Okay. All right, good deal. We'll see you Wednesday.